So for our project, we dealt with adventitial tissue analysis in coronary atherosclerosis as a continuation from a previous year's project. We had 5 team members, Westin, Danielle, Vanessa, Katherine, and me, Sean Ewalt. We had 2 mentors as well, Dr. Schmid-Schonbein and Dr. Elliot McVeigh. So just to provide some background information for our project, coronary atherosclerosis is characterized by the buildup of calcified lesions or plaque on the arterial wall of the blood vessels of the heart, and this leads to vessel stenosis or blood flow restriction. The disease is so widespread that it contributes to 50% of all deaths in Western society. But despite the pervasiveness of atherosclerosis, the etiology behind it is still relatively unknown. As a result, despite the existence of relatively effective early stage treatments such as statins, poor risk report construction leads to such therapeutics being applied at too late a stage where the progression of atherosclerosis is irreversible. Most research on this topic focuses on factors inside of the vessels, such as blood flow abnormalities at vessel bifurcations. Although there does appear to be a correlation between lesion development and vessel bifurcations, this hypothesis fails to account for plaque buildup in regions unrelated to blood flow perturbations. As a result, there's been a push for research on factors outside of the blood vessel that look at the effects that tissues surrounding the lesion site can have. So there's still limited technology to assist researchers for this method of analysis, which led to our development of an image processing system that could draw correlations between surrounding tissue types and lesion existence. This innovation could potentially help determine the etiology of atherosclerosis, resulting in superior risk report construction, which could further save thousands of lives.
The design we created is a MATLAB algorithm that uses an input of a semi-manually segmented cardiac CT scan that include both an artery with stenosis as well as tissues that surround it. The program then linearizes this vessel and analyzes it to deduce the respective positioning and amounts of the tissue types. The outputs include a qualitative tissue map that allows for users to visually identify the tissue types surrounding the vessel, as well as the extent of plaque buildup. Additionally, there will be a quantitative output that determines the percentage of tissue types in the segmented region outside of the vessels, while also determining their distance from the lesion.
As a continuation on this same project that a team worked on last year, our main goals were to better organize the process in which we go from scan to segmented vessel to loading the image into MATLAB, and to try to improve the runtime and accuracy of the analysis functions. We have succeeded with the processing and loading steps organization, as our team has clearly outlined the pipeline to both find and segment vessels, as well as easily load the necessary files into MATLAB. We have also succeeded in both the development and refinement of the TID function and the tissue distribution function. Especially with the distribution calculations, our function runs quickly and outputs the percent composition of different tissue types. Unfortunately, we haven't been able to improve either of the qualitative analysis steps. The major bottleneck here is the use of a MATLAB package to aid in linearizing the vessel, which is a very time-consuming step that trivializes any improvements to be made with the normal plane identification. Regarding the tissue mapping, the current function has been written to handle linearized input. So without the completed linearization step, the color mapping is very inaccurate and difficult to visualize within the volume viewer. For immediate future work with this project, these qualitative analysis steps will be the focus of future teams that work on this project. The long-term goals of this project to be carried out by future teams is to be able to use the concentration calculations to determine if correlations can be made between not only the tissue distribution along the full segmented vessel, but also to determine if distance from the lesion along the vessel has any impact on the tissue composition. For example, one may compare the tissue composition of healthy vessels or a portion of the vessel with no lesions with the average distribution directly around the lesion sites. Another long-term goal is to combine the sub-projects together into a cohesive script to get closer to fully automating the process. Within the next few years, we hope this project can help researchers continue to understand the etiology of atherosclerosis. This could potentially lead to further development of a diagnostic method that can be used to determine if a person is showing signs of an atherosclerotic site well before the lesion actually develops. Thank you very much for your time.